All right, guys, welcome to 707 part 3, where we're going to wrap up sliding filament theory. We left off with step 8, where steps 7 and 8, calcium binds to the troponin complex, and that causes the tropomyosin moves, which exposes the binding site. So once that binding site is exposed, this is that phosphate group, PO4 is phosphate, or just a P. The phosphate group leaves, and this causes the myosin and actin to bind. Now, notice direction means everything in sliding filament. Notice that there is a 90-degree bend between this myosin head and the actin. This is the ready position, because what's going to happen is this angle is going to decrease and the myosin is going to pull up towards the fiber. And what's going to happen is, so as this myosin moves, it's going to pull the actin this direction. And that's what happens here. So here, and that's a little bit small, but that's the ADP. So this is called, step 10 is called the power stroke. This is where we actually move. Whoops. There we go. So this was red. So we go from this 90-degree position to this this angle is like what, like 20 or 30. And it's that rotation towards the inside that moves this actin filament this way during the power stroke. And this is accomplished by the ADP leaving the myosin head. So we have ADP leaves the myosin head, causing the myosin to rotate to center. So this in turn, this doesn't move. The only thing that moves is this myosin head, but the whole actin fiber is pushed towards the center of the sarcomere. So every time and every myosin head that moves requires an ATP. You can see what a huge amount of ATP we're going to need. So that leaves the myosin head is still bound to the binding site, and it's empty. In order to get it to release, we have to have, now this is an ATP. Remember the whole circle was an ATP? So the next step is step number 11. An ATP binds to the myosin head. And this causes it to release. So step number 12 is the myosin head detaches from the binding site. If this is the end of if the muscle's done contracting, what will happen is we have one of two things that can happen here, and there should be an arrow here. That arrow. Why did that out? So at the end of a muscle contraction, the calcium will get taken back up into the sarcoplasmic reticulum. So we're assuming we're at the end of a contraction. So step number 13 is calcium is taken back into the sarcoplasmic reticulum. causing the tropomyosin to move back over the binding site. Now, if I have calcium present, what I'll do is I will go from, so if calcium stays, if we keep that flood of calcium coming, I'll go from this step to this step, and the binding site won't cover back up. So if I have calcium present, and I'll just loop. But then when I'm done, that calcium isn't wasted. It's taken back into the sarcoplasmic reticulum, which is what we see here. And without that calcium in place, the troponin pulls that tropomyosin, and now the binding site's covered back up. You see that's covered, it's blocked. So now here at step number 14, the muscle fiber is at rest in a sense, but you'll notice I don't have that 90-degree angle. Well, how do we get that? So this is an ATP, but you'll notice over here when I started, I had an ADP and a P. So to get that, what will happen is that ATP will split into ADP and phosphate. And that will put the myosin head back into this 90-degree ready position. So putting the myosin head into the ready position. Sometimes people call this, if you think about, if you've ever shot a gun that has to be cocked, you have to pull that hammer back. And then once that hammer's back, you can fire it at any point, but till the gun is cocked, it won't operate. And so that's what we have here. We have, this is a myosin head that is not in the right position. And when I split that ATP into ADP and phosphate, now it is. And then we're ready to go back to the nerve impulse. So now we're waiting here. And at we'd go back to step 1, the nerve pulse would come in, and we go all the way around the loop again. Whole kit and caboodle. So let's watch the video again, and then I'm going to go to a summary page. Oops. Got to hit a button that I need. Share screen, share computer sound, share, max, and play.
Contraction of skeletal muscle tissue occurs when actin and myosin myofilaments slide past one another, causing the sarcomere to shorten. It is important to note that the individual myofilaments do not change length themselves, but instead overlap each other to shorten the sarcomere. Moving in for a closer look, we can see the details of how this occurs. The molecules you see here are myosin, which at rest has both adenine diphosphate and phosphate molecules attached at the individual myosin heads, actin, tropomyosin, and troponin. When we decide to move, calcium is released from the sarcoplasmic reticulum. These molecules bind with their troponin molecules. This causes the tropomyosin molecules to move, revealing myosin attachment sites on the actin myofilaments. The single phosphate attached to the myosin heads gets released as the heads move to connect with the attachment sites on the actin. The resulting formation is called a cross bridge. The remaining adenine diphosphate molecule is then expended in what is called a power stroke, when the myosin heads pull the actin inward. Once the adenine diphosphate attachment is spent, adenine triphosphate molecules attach themselves to the myosin heads. These molecules trigger the release of the myosin heads from the actin attachment sites and are immediately broken down into adenine diphosphate and a single phosphate as the heads move back into their resting position. This is called the recovery stroke. If calcium is still present, the cycle will repeat again, and the sarcomere will continue to shorten until the calcium ions are transported back into the sarcoplasmic reticulum and the muscle relaxes.
Okay, so let's wrap up with this summary page. So if we look, we can kind of look at this in a different way. So steps 7 through 8, the contraction cycle continues. So we have calcium levels in the sarcoplasmic reticulum are high. So this is steps 7 and 8, and the calcium leaves the sarcoplasmic reticulum. Well, yeah, I don't want to move my page again. So here is step 9, where that phosphate group is leaving and the myosin head attaches to the actin and we form the cross bridge. And notice the ADP is still attached at this point. Now the ADP leaves and I've gone from a straight up and down. So I've got kind of a, it doesn't show quite as well here, but my angle has changed. So my theta has become less and the ADP leaves, which rotates towards the center. And this we said was step 10. Over here, now I have an ATP coming in and it's going to break. So the ATP coming in is going to break that attachment. And so that causes the actin and the myosin to detach. And we said this was steps 11 and 12. And then finally, if we come up here, the myosin had split ATP to become reoriented and energized. We said that was the last step. So we said that was step 14. So this is a summary of the phases of the what's going on with the actin and myosin, not necessarily with the nerve impulse, but it kind of gives you a different visual. So just to sum up from steps 1 all the way back through, we start off, we have a nerve impulse that arrives in the axon terminal. It causes the release of acetylcholine. Acetylcholine binds to the receptors on the opposite side of the synaptic cleft. The receptors cause the sodium to flow down into the T tubules. The sodium in the T tubules causes calcium in the terminal cisternae to be released into the sarcoplasmic reticulum. The release of calcium from the sarcoplasmic reticulum occurs. The calcium binds to the troponin. The troponin moves the myosin, tropomyosin. Now the binding site's exposed, so the phosphate group leaves, which causes the myosin and actin to bind. Then the ADP leaves, the ADP group leaves, which causes the myosin head to rotate to center, pulling the actin fiber towards the center of the sarcomere. Now we have ATP coming in to detach the myosin head from the actin. And then finally, if we're at the end of a cycle, the troponin and tropomyosin move back over the binding site as calcium leaves. And finally, that ATP on the myosin head gets split and puts the myosin head into the ready position. So that is the sliding filament theory, and that is the last video. So we are all done. Thanks for watching.